Hello everyone. Welcome back to our VulnHub walkthrough series. In today's video, we'll continue exploring the exciting VulnHub collection with Symfonos. Specifically, we're diving into the fourth virtual machine in the series, Symfonos 4. This intermediate OSCP-like real-world scenario machine is designed to emphasize the importance of understanding vulnerabilities and how to exploit them effectively. Let's get started. To begin, first head over to the VulnHub website and download the machine's image file. If you're new to VulnHub, make sure to check out our playlist for helpful guides on how to use the platform. Now, let's jump right into exploiting this machine. Setting up. Previously, we downloaded all 6 image files. Our next step is to set up the virtual image in VirtualBox. The downloaded image file is in 7Z format. So start by extracting the archive to access the files within. Here, I found an OVA file, which is an essential extension used by VirtualBox for direct imports. Next, we'll import this virtual machine. To do this, double-click on the OVA file. This will automatically launch VirtualBox and display the Import Virtual Appliance wizard. In the wizard, you can adjust or modify the settings as needed. For better organization, I'm going to modify the primary group to the VulnHub group. Once you've made any necessary adjustments, click on Finish to complete the import process. After completing the setup, you'll see the Symfonos 4 vulnerable machine listed in the VirtualBox Manager. Now, we need to configure the network settings. To ensure both your Kali Linux machine used for attacks and the vulnerable machine are connected to the same network, set their network adapters to host only. Go to Settings, and under the Network tab, change the adapter to host only. Once everything is ready, start the virtual machine to confirm that it's working properly. After launching the virtual machine, you should see a login prompt, confirming that everything is set up correctly. Now we're ready to begin our exploration. Start by launching your attacking machine, which in my case is Kali Linux. With Kali up and running, it's time to dive into the fun. Enumeration. The first step in our attack is enumeration, where we identify the IP address of our target machine using the NetDiscover tool. This step helps map the network and locate devices that are up and accessible. To execute this, open a terminal and enter netdiscover-i, then specify the network interface to use for scanning, which in this case is ETH1. The command output displays a list of devices detected on the network, showing their IP and MAC addresses, as well as the associated vendor. Our target machine's IP address is identified as 192.168.103.16. Next, we'll perform a network scan to identify open ports on the target, which is a critical part of the enumeration process. Identifying open ports provides insights into the network's attack surface, helping us pinpoint services that may be vulnerable to exploitation. For this task, we'll use the popular network scanning tool, Nmap. To execute the scan on the terminal, run nmap-s, capital C, -s, capital V, then specify the target IP address. In this command, -s, capital C, initiates a script scan using Nmap's default scripts, which gather additional information about each service and identify possible vulnerabilities. -s, capital V, enables version detection to determine the version of services running on open ports. Once the scan completes, the results reveal 2 open ports with their respective services. Port 22, TCP, is running SSH, or Secure Shell, which provides remote access if valid credentials are available. Although SSH is generally secure, weak or default passwords could make it exploitable. Port 80, TCP, is running HTTP on a web server. The scan shows a basic website with no title, hosted on Apache HTTPD. This service is a common entry point for attacks and may contain web-based vulnerabilities. These open ports present potential entry points into the target system. The next step is to conduct a deeper enumeration of each service to uncover vulnerabilities or clues that could facilitate initial or shell access. This focused analysis will guide us in developing a strategic approach to compromise the target. Our next steps involve identifying vulnerabilities to gain shell access or other footholds on the target system. Since the HTTP web server is running on port 80, we'll begin by analyzing it, as web services often serve as primary access points that can reveal additional attack vectors. Access the web service by entering the target's IP address directly into a web browser. The web page displays an image resembling Poseidon, the Greek god of the sea, with a prominent trident symbolizing his power. Upon inspecting the page source, I did not discover any hidden clues. To locate hidden resources, we will perform directory enumeration using tools like darb or GoBuster. These tools systematically probe for common directory and file names that are not directly visible on the website. This process can uncover sensitive files or directories that aid in further exploitation. Execute the following command in the terminal. Here, GoBuster dr initiates directory enumeration. -U is used to specify the target URL, and -W is used to specify the word list for the scan. During enumeration, we discovered a directory named gods. Opening it in the browser reveals an index containing files named Hades, Poseidon, and Zeus. These file names suggest a theme related to Greek mythology or fantasy. The .log extensions indicate the files may contain log data associated with activities or processes. Upon inspecting these log files, I found information related to the god. However, this information is not very helpful, so we will perform directory busting again to check if it may contain additional files. To refine the enumeration, we will use GoBuster's -X option to filter by extensions such as .php and .html. This revealed two accessible files, /index.html and /atlantis.php, both with a status code of 200. Additionally, /c.php redirects to /atlantis.php, indicating linked functionality. Inspecting /atlantis.php, we discovered a login portal that could serve as a potential entry point. Initial attempts to log in using default credentials like admin, admin, and admin password were unsuccessful. However, based on the behavior and structure of the login form, I suspect the website may be vulnerable to SQL injection. To confirm and exploit the SQL injection vulnerability, we carefully observed the server's response to various SQL payloads. We attempted to bypass authentication by entering the following payloads. Open single quote space or space open single quote 1 close single quote equals open single quote 1 close single quote. Initially, these attempts were unsuccessful. However, after appending a hash mark at the end of the payload to comment out the rest of the SQL query, we successfully bypassed the login form. Upon successful login, we discovered a drop-down menu labeled Select a God. The options in the drop-down are Hades, Poseidon, and Zeus. It's not immediately clear what functionality is triggered by selecting one of these options. Upon selecting an option from the drop-down, it displays information related to the chosen god. For instance, selecting Zeus leads to the display of details about Zeus. Notably, this behavior aligns with the text previously observed in the gods directory during directory enumeration. It appears that when a god is selected from the drop-down menu, the application dynamically retrieves and displays content from a corresponding file. Examining the URL structure provides a critical clue. The parameter file equals Zeus suggests that the application retrieves files based on the value of the file parameter. This behavior indicates a potential local file inclusion (LFI) vulnerability, as it may allow arbitrary file inclusion. The next step is to confirm and exploit the LFI vulnerability. To test for LFI, we will modify the file parameter in the URL to include a relative path to other files. However, this did not display the contents of /etc/passwd. This outcome could be due to one of two reasons. Either the application may not be vulnerable to LFI, or a valid and accessible file path needs further investigation. To investigate further, I hypothesized that the application might restrict paths using // sequences. Instead, I will try using // which represents the current directory. By modifying the file parameter to /Zeus, I was able to successfully read the content of the Zeus file. Building on this success, I attempted to access /etc/passwd, again using this approach. Unfortunately, this attempt was still unsuccessful. This suggests that either the file path is explicitly restricted, or additional filtering mechanisms are in place, preventing access to sensitive files like /etc/passwd. To systematically explore further, I will consider additional methods, such as inspecting for potential encoding requirements or using fuzzing tools to identify alternative file paths that may bypass these restrictions. To brute force the file paths, we will use FUF. But before, we need a few things to perform FUF. We will need a cookie, and we also need a word list. Since the LFI vulnerability is being tested within a logged-in session, a valid session cookie is required. Without the cookie, FFUF will treat the page as inaccessible due to the lack of authentication. Open the browser's developer tools, usually by pressing F12, navigate to the Storage or Network tab, and copy the session cookie. First, we need to arrange the session cookie systematically to ensure authenticated access during the brute forcing process. For this task, we require the Cyclist LFI word list. However, it is not pre-installed in Kali Linux, so we must download it from GitHub. Next, we execute the following command for brute forcing. -u specifies the target URL with FUZZ as the placeholder for brute forcing. -b provides the session cookie for authentication. -w points to the word list used for testing file paths. -c enables colored output, making the results easier to interpret. Initially, the output included many results, most of which were false positives. To improve efficiency, we analyzed the output and observed that standard error pages contained 56 words. Using this information, we refined our search by adding the -fw flag to exclude these irrelevant responses. After filtering, the refined command successfully displayed valid files. One critical file identified during this process was /var/log/auth. This file could potentially provide further insights or information useful for exploitation, and it will be the focus of the next phase in our investigation. Exploitation. To exploit this, we will insert the file path into the LFI section. By inserting this file path into the URL, it displayed the SSH login attempt logs, which provided valuable information for further analysis. Log files can sometimes be exploited through log poisoning, a technique where malicious input is written to logs and later executed by the application. To test this, we attempted to inject a simple test string, hello world, as a username. To verify log poisoning, open a terminal and execute the command SSH, hello world, at 192.168.103.16. When asked for a password, press enter without providing one, since we do not have valid credentials. Next, refresh the /var/log/auth log page. The log displayed the username, hello world, along with the message, connection closed by invalid user, hello world. This confirmed that our input was being recorded in the log file, validating the presence of a log poisoning vulnerability. The next step was to inject a remote code execution payload into the logs. The goal was to execute malicious PHP code that would provide a reverse shell, granting a foothold on the target system. However, upon trying to inject SSH poisoning, the server displayed an error message. Remote username contains invalid characters. This error occurred because the SSH invalid character vulnerability had been patched in newer versions, preventing exploitation through direct injection. Given the patched SSH validation, we switched to Metasploit for automated exploitation. To inject RCE with Metasploit, launch MSF console from the Kali menu. Search for the appropriate SSH module. Two auxiliary scanner modules were displayed. We selected the auxiliary/scanner/SSH/SSH_login module. Now we have to check for the options for the selected module. Here, we need to set the R hosts to define the target system. Next, we will set the username field, where we will inject the previously used RCE code. Since we do not have a valid password, we used a demo password of our choice. Execute the run command in Metasploit. The auxiliary module executed successfully, confirming that the RCE payload was injected. Now it's time to exploit the RCE payload. Open a web browser and navigate to the vulnerable parameter URL. Modify the URL to include an ampersand symbol, followed by the CMD parameter as specified in the RCE payload. Use an equal sign to input the command. For example, modify the URL to include &CMD equals ID. Upon running the ID command, the server responded with connection details, including the GID, group ID, and UID, user ID. This confirmed the successful execution of commands on the target system. Further steps involve leveraging the reverse shell to gain access to the target system, escalating privileges, and exploring additional vulnerabilities or sensitive data. Foothold. The next step is obtaining a reverse shell to gain a foothold over the target system. To establish a reverse shell, begin by preparing a listener on your machine. Open a terminal and use netcat NC to set up the listener by specifying a port to listen on. Next, inject the reverse shell payload into the vulnerable URL. Modify the CMD parameter in the URL to execute the reverse shell payload using netcat. Use the command NC followed by specifying the listening host IP. To determine your local IP address for the payload, run the ifconfig command. With the local IP and port identified, now specify a listening port. Use the -E flag to execute /bin/bash as the command. Once the payload is executed, verify the connection by observing the terminal running, netcat. A connection message confirms that the reverse shell has been successfully established. To make the shell fully interactive, check if Python is installed on the target system by running which Python. If Python is available, use the pty.spawn method to upgrade the basic shell obtained from the reverse connection to an interactive tty shell. This allows the use of terminal features such as tab completion and command history. The shell is now more stable and interactive, improving usability for further exploitation. Now, we need to explore the target directory. List the files and directories in the current working directory /var/ww/html using the ls command. The files in the directory include atlantis.php, which is likely related to the web application, and other supporting files, such as CSS, JavaScript, and index.html. There is usually a chance of sensitive information being left in the application code. To investigate further, examine the application code of the atlantis.php file for potentially sensitive information. This reveals the application's backend logic, including database credentials. With these credentials, attempt to use the suroot command to switch to the root user. If the authentication fails, it indicates either incorrect credentials or that the credentials are for a non-root user. Upon trying the credentials, we received an authentication failure message. This indicates that either the username-password combination is incorrect or the username itself may be incorrect. To identify potential users, we examine the system's /etc/passwd file, which contains a list of all user accounts. We use the cat command as follows. Among the accounts, we noticed a non-root user named Poseidon. Suspecting this user might be associated with the application, we decided to attempt switching to the Poseidon account using the database password. To do this, we use the su command, which stands for substitute user, to switch to the Poseidon account. Upon entering the database password, the password was accepted, and we successfully switched to the Poseidon user. Now, operating as Poseidon, we navigated to the user's home directory to check for the user flag. We searched the directory and its subdirectories, but found no flag. Since no flag was located in Poseidon's directory, the next logical step is to perform privilege escalation to obtain higher-level access. Privilege escalation. In the privilege escalation process, the primary goal is to enumerate the system further by identifying potential misconfigurations, exploitable vulnerabilities, or overlooked permissions. Our focus is to search for files or processes that may allow us escalation to root or another privileged user. Additionally, we will investigate permissions, SUID files, running services, and scheduled tasks for potential exploitation opportunities. As we currently operate with limited user privileges through the reverse shell, we face restrictions on accessing certain files or commands needed for a comprehensive assessment. To move forward, we run the sudo-l command to check if the user Poseidon has any sudo privileges. The result indicates that the Poseidon user either lacks sudo privileges or the sudo utility is unavailable in their environment. Next, to gather more details, we run the id command, which provides the user's UID, GID, and group memberships. Poseidon is identified as a regular user with UID equals 1000 and no root level privileges. However, under groups, Poseidon is part of several groups such as audio, video, CD-ROM, DIP, and plugdev. Notably, the DIP or Dial-Up Internet Protocol group permits managing network connections, which includes tunneling or VPN setup. This points to a potential relevance, where Poseidon's group memberships may allow setting up reverse SSH tunneling, port forwarding, or privilege escalation through exploiting network configuration permissions. To investigate further, we run the ss-tuln command to analyze open ports and identify possible services running on the system, revealing various open ports that may assist in privilege escalation efforts. In these open ports, ports 22 and 80, previously identified via Nmap, are accessible externally. But the other two open ports, port 8080 and port 3306, are bound to the localhost IP address 127.0.0.1. This indicates services restricted to internal connections. Port 3306 seems to be running a database service, while port 8080 is potentially an internal admin panel or web service. Due to their restricted nature, these services are inaccessible directly from an external system. However, by leveraging SSH tunneling, we can expose these services to our attacking machine. To bypass the localhost restriction, we used SSH tunneling to forward traffic from the target's internal services to our machine. The process involves creating a tunnel from our attacking machine to the target system. For port 8080, which likely hosts an admin panel or another internal service, we forward it using the SSH client tool. Here, the -l flag is used to specify local port forwarding, which forwards local port 8080 on our attacking machine to the target's internal port 8080. Once the tunnel is established, we can access the service on port 8080 by opening localhost:8080 in our browser. This allows us to interact with the internal admin panel or service as though it were hosted locally. Now it's time to access the forwarded service from our browser. Navigate to localhost:8080. Upon accessing 127.0.0.1:8080, the page redirected to 127.0.0.1:8080/WOMI, displaying the message cookie set Poseidon. Additionally, the page provided a link labeled main page, which appeared to lead to another section of the site. Clicking on the main page, link revealed a simple, likely personal or test website. The page featured an image of Poseidon, the Greek god of the sea, holding a trident. A welcoming message, "Welcome back, Poseidon." The previously displayed message, cookie set Poseidon, suggests that the cookie may contain exploitable information or be useful for session hijacking. To investigate further, we accessed the browser's developer tools, navigated to the storage section, and inspected the cookie. There are 3 cookies listed. Among these, the second cookie value string looks suspicious. This string resembles base 64 encoding, potentially holding critical information about the user session or application functionality. To understand its contents, we used a base 64 decoder to decode the cookie. The decoded output revealed curly brace pi/object::app dot, user, username, Poseidon curly brace. The decoded cookie contains the following information. pi/object::app.user indicates the object belongs to a Python-based application, likely serialized with Python's pickle module or a similar library. Username:Poseidon confirms the username associated with the current session. This serialized data suggests a potential vulnerability to deserialization attacks if the server lacks proper validation mechanisms. Such attacks could enable privilege escalation or arbitrary code execution. To test this vulnerability, we modified the username field in the cookie to see if it allows impersonation of other users or privilege escalation. After editing the username, the manipulated cookie was injected back into the session via the browser's developer tools under the storage section. The server accepted the altered cookie, confirming its vulnerability to serialized object manipulation. The modification was successful, and the application accepted the manipulated cookie. This indicates that the server is vulnerable to serialized object manipulation, opening a path to inject a malicious payload for further exploitation. Now we look for opportunities to exploit the cookie by injecting malicious payloads into serialized Python objects, using shell commands to trigger a reverse shell. To proceed, it is critical to understand the JSON structure and how the serialization mechanism, such as JSON pickle, works. This library supports complex Python object serialization, including custom classes and functions, making it susceptible to exploitation if improperly implemented. The exploitation process begins by crafting a malicious payload designed to execute commands during deserialization. The payload uses the os.system function to establish a reverse shell connection. A serialized JSON object is constructed with the following structure. In this JSON structure, you must specify the attacker's IP and listening port in the payload to ensure it targets the attacker's machine for the reverse connection. To inject the malicious payload into the vulnerable application, serialize the JSON object. Encode it using base64, as the application expects the cookie in this format. With the payload prepared, replace the original cookie value in the application session with the base64 encoded malicious payload through the browser's developer tools under the storage section. Before triggering the payload, set up your machine to receive the reverse shell connection. Open a terminal and start a netcat listener using the command nc-lvnp4444. Next, perform an action that forces the server to process the manipulated cookie, such as refreshing the page. When the server deserializes the payload, it executes the malicious code, triggering the reverse shell and establishing a connection to the attacker's machine. Once the payload is executed, the reverse shell connection becomes visible in the listener terminal. To enhance usability, upgrade the shell to a fully interactive TTY shell. Use Python for this by running python-c import pty pi.spawn open parentheses double quote /bin/bash double quote close parentheses single quote. This upgrade enables terminal features such as tab completion and command history, providing a stable environment for further exploitation. Upon confirming the connection, execute the uomi command in the shell. The output confirms that the current user is root, validating the successful privilege escalation. The next step is to locate the root flag, typically stored in the root directory. Change to the root directory by running cd/root. Here, we found the root flag, proof.txt. Use the cat command to view its contents and complete the challenge, cat proof.txt. This marks the successful conclusion of the attack. If you have any questions or need further clarification, feel free to leave a comment. If you have any doubts or queries, write them in the comments section.